The government takes care of it. So, there are 3 stage selections, 2 stage training, and we partner with teacher organizations a lot. Go to the next slide. So, there are 5 stages. So, sometime in November, last weekend of November typically, is the first level, what is called the National Standard Examination in X. Okay, NSE, physics, chemistry, biology, junior science, astronomy, whatever it is, and the Indian Olympiad qualifier in mathematics. Mathematics is a slightly different thing. This is the science one. Okay, so that is taken by around 2 lakh students, 800 centers across the country. We do not do it. This is the only stage which is done by the teacher organizations, and it's done, the academic oversight is ours, but it's done by the teacher organization. Then from that, from 2 lakhs, it becomes 2,000 who give this exam called the Indian National X Olympiad exam, INPHO, INCHO, etc. That happens end of last weekend of January or first weekend of February. From that, 2,000 people who give it, around 200 people are selected for the third stage, which is the orientation of selection camp. These are going on right now. This is April to June, this window. From these camps, we select the teams. Some subjects 4 students, some subjects 6 students, 5 students, whatever it is, who will represent India. They come back, there's a pre-departure camp for them, and then they go to the International Olympiads in July, except the Junior Science Olympiad, which is December. Okay, now, for us this is a year-long thing, because it's not just the Olympiad. You have to plan interesting experiments, interesting questions, so it's a year-long activity for us. It's much beyond the exams. Go ahead, Asha, please, go ahead. We work with students, we work with all kinds of students, we work with all kinds of teachers. Go ahead, please. Who is eligible? You must have the government has said that you must have an Indian passport, you must be an Indian citizen to represent India in the International Olympiads. You can participate in this, even if you are not, you can participate up to the OCSC, you can come to the camp, but you cannot get selected for the team if you are not an Indian citizen. Okay. Age is between 14 and 20 years for the senior Olympiad, between 13 and 15 years for the junior science Olympiad. You must be in class 10, 11, 12 for the senior Olympiads, 8, 9, 10 for the junior Olympiads, junior science or junior astronomy. You must not have either passed class 12 or class 10. You must be a pre-collegiate student. Okay? And you can enroll directly in some places through your school, and you can give the exam in many subjects, no problem. But you can choose only one for, if you get selected, you have to choose which one you will come for. Okay. The syllabus is mostly CBSE class 10 or class 12. Go ahead. Okay. The first stage is not conducted by us. It's conducted by the Indian Association of Physics Teachers, Association of Teachers in Biological Sciences, Association of Chemistry Teachers. Of this, IAPT is the biggest, so they coordinate the whole thing. The chemistry and bio people give them the questions, but IAPT runs the show. Okay, so you can register in August or September, or at your or something. Anyone can participate. This is the only level which has a fee. $300 is what they charge. We don't. They charge. Okay, and we had around 240,000 people who took the exam last year. This is an MCQ with negative marking. It's an MCQ because that's the only way we can correct 250,000 papers. Okay, and this happens on the 3rd and 4th Sunday of November. It depends. The results are announced on the 1st in January. And you are given a copy of your results, of your OMR sheet. So there is no thing that मैंने B tick किया लेकिन answer C है, all that matter doesn't happen because you got a copy of your paper. If you want to challenge it, you can, but then we will compare it with the paper you have. Okay. From this, there are 2 ways of getting to the next level. Anybody who scores beyond a certain threshold is into the next level. Okay. Otherwise, there are regions, because it's a government program. We have to encourage people from all regions. So there is we don't go by the scorer of the topper. The topper might be some crazy guy. We go by looking at the top 10 scores. So you take the average of the top 10 scores. 80% of that is the merit index. Anybody getting more than 80% of the average of the top 10 scores is in. There is also the minimum acceptable score. If you take the average of the top 10 students, 50% of that. Anybody who gets 50% below 50% of that is out. They don't get it. In the middle, we go region wise. In every region there is a certain quota. If it is already filled with the merit people, no need to go ahead. If not, you take the next people as long as they are above the minimum score. After that, if you don't have enough girls in everything, you add more girls to it as long as they are above the minimum score. Right? So we try and do this because this is all anonymous at this stage, so there is no quota as such, but we can do it. Then from that, you have to register for the Indian National Olympiad. This is mostly long answer type questions, except in biology, which is objective. Mostly these are long answer type questions. Some of the questions are based on experiments also, though we cannot do experiments, but we do. India does very well in theory. Our problem is experiment, because most of our kids don't know how to do experiments. Okay, so we have some questions based on experiment to at least try and make them think about how experiments are done. This happens in January, and then after this, once the results are posted, you can say, "Nee, I answered it this way, my answer should be correct," we will listen to you. We will give you a fair chance. So there's a chance for arbitration, there's a chance for challenging, etc. And then it is merit based, and we take the top 20 students from class 12, the top 20 students from 10, 11, and invite them for the camp. Astronomy takes 15 and 35, and this happens for the next stage, which is the camp. The camp, which is going on right now in various subjects, 35 to 50 students come, they are given lectures on various theoretical aspects, they do experiments, there are multiple exams during the camp, after which we select the team. Go ahead. So there are multiple exams, then depending on the thing, 4 to 6 students are selected, go ahead. Then these people come back before 1 week before they leave for the International Olympiad, they come back to TIF, to HBCSE, where they are given the final polish. They do more experiments, they do more theory, whatever, and then they go with their mentors for the thing. Now, at the international level, please remember, if the Olympiad is being held in Uzbekistan, the questions are prepared by Uzbekistan, except maths. Maths is an international board that prepares the questions. Otherwise, questions are the responsibility of the host country. The host country might be very small, they might request help from others, that's okay, but it's their responsibility. Okay? But the international jury agrees that these are fair questions. Which is why when you go to the International Olympiad on day 1, you will be separated from your mentors. Because you will be in a separate place, the mentors will see the question paper. They know the question paper before you have done it. Because the question paper officially is in English, but it gets translated to all the, Bangladesh translates to Bengali, China translates to Chinese, whatever else. So they have to translate the paper. So while you are sleeping, they are translating the paper. The next day you are giving the exams, they are sleeping. The moment you give the exam, the paper comes back and gets xerox. One copy is corrected by the host country, one copy is corrected by your mentors themselves, because the host country may not understand everything that you've written. Maybe you've written something that they didn't understand. So host country wants to give you minimum marks, mentors want to give you maximum marks. So then they have a session for arbitration where they decide the final marks, then they decide the medals, etc., etc. We do very well. Now, in general, only the top 10% gets gold. But in India, 40% of our students get gold. Top 12% get silver. This is for the various subjects. Typically, silver is 20% or so. Top 10%, 20%, 25%. For us, it's 40%, 42%, 12%. We hardly get bronze and honorable mention on all these things. Okay, so this is how it has been. We do very well in the international Olympiads. Go ahead. We also go ahead. This one, yeah. So after coming back, most of the Olympiad people who have represented India have done fantastically well in science wherever they are across the world, including back to India. Many of them are professors across India now, and they help us with running these Olympiads. Go ahead. We also host Olympiads. We hosted all the Olympiads right from chemistry in 2001 till astronomy last year. We hosted all the Olympiads in India, and it's been a great thing that we have also. People recognize that some of the best Olympiads have been hosted by us. Okay, keep going. And we have various books and all about problems which you can get online. You can get from the HBCC library if you want. You can ask the school library to get it. And we are going to have more. We plan to have more than just this, even compilation of experiments, kits that you can get, etc. But that's just there. Now, the Olympiad involves teachers from across the country. You can see the dots across the country. Teachers from across the country help us do these Olympiads. Okay. And they help in many stages. Go ahead. Now, just remember that this is fully supported by the Department of Atomic Energy mainly, but also by DST for science and for physics and chemistry, Department of Space for astronomy, the Ministry of Education pays the price for the tickets for going to the foreign thing, etc. And we do a lot of stuff with this. Go ahead. Now, of course, there's other things at HBCSE beyond the Olympiads. Once you go to college, you can come for the National Institute of Undergraduate Science. There's also Vigyan Vidushi for women, there's Vigyan Pratibha happening at the school level, lots of things are happening. We keep going. So now, let's get to science. Okay? Hold on to this slide and don't go ahead. Okay, so now just remember that we will do some experiments, and during these experiments, the main thing is you should appreciate what is science. Okay, what is science? What is science? Somebody please tell me what is science. Everything around us is science. Just that's it. That's it. Just everything around us. We don't have to bother interact with that.
Sir, the study of world around us, sir.
The study of the world around us. We can be studying it. What are you doing? Observing and understanding. So science is our effort to observe. Thank you so much. Observe and understand the world around us. That world around us can be the world inside a cell in my body. It can be the world inside a leaf on the tree outside. It can be the world around a star in a galaxy far away. Science is our efforts at trying to systematically observe and understand. We can observe, sometimes we can understand, sometimes we can't understand. The thing is, every time we do this, it gives us more questions. It gives us more questions that we can ask, and that's how it develops. Okay. Now, and this is very important for the Olympiads, the real world is very complex. We cannot understand the real world if we try to understand everything related to it. So we make simple models of it. Simple models, you focus on what is important. So Ravi, IPL chal raha hai, right? So in IPL, you see this time it's becoming a batter's paradise. You see a batter just whacks something and it goes for a 6. Yes? Okay. You follow a little bit of cricket at least. I play badminton usually, but itna to pata hai ki IPL mein everybody is banging 6s. Now if a ball comes and I hit it for a 6, I cannot take into consideration all the parameters. I have to decide which are important, which are not important. Is the color of the ball important?
No.
Is the force with which I hit it important?
Yes.
Is the direction in which I hit it important?
Yes.
Is the color of the grass important?
No.
So you see, why did you say no? Why did you say no to the color of the grass? Is the air resistance important?
Yes.
Maybe. See, for a simple model, initially I may say that, look, I'm going to ignore air resistance. I will put that correction later when I want to make a better model. Do I need to take into account the stitching on the ball?
Maybe.
Initially, no. If I want a very exact model, maybe the stitching is what makes the ball turn, etc. I may want to keep it. Okay. So models slowly become. So in physics, what do? In physics, sometimes you'll have some complex system. A train is moving, a car is moving. You think of it as just a point with a mass m which is moving with a certain speed. You ignore the details. Right? In chemistry, you will show atoms as some balls and sticks and all connecting them. What we know, atoms are not balls and sticks. But it helps us understand that this bond broke, it went there, this atom went to that thing, it's something. Biology, they show cells as some diagrams. They keep only the part that is interested. If I'm not interested in the mitochondria, I will not draw it. Okay, so when you ignore the details, it's not a mistake. It's a way of using our limited understanding to focus on what is important. Okay, and this allows us to predict things, and prediction is a very powerful tool of science. It's one of the hallmarks of science that we can predict things. Okay. Now go ahead. I don't know. Okay. Now again, please remember that scientific theories are not perfect. They are perfect. They are based on what we know till now. Every time we know more things, new experiments happen, we update our theory. Sometimes when we find something doesn't match, we say this theory can be improved. It's not that the earlier theory was necessarily wrong. So you had Newton's theories of motion. They work perfectly well for cars, buses, trains, rockets, whatever. Okay? When you get to speeds which are very high, then you need corrections because of Einstein. But it's not that Newton's theory was wrong. Einstein's theory came later, it gives you a correction to it, and you get it made, something like this. So, this is a hallmark of science that we allow ourselves to be corrected. It's okay to make mistakes. It's absolutely okay to be wrong. It's absolutely okay to come up with something which gets then changed later on. That's part of the process of science. Okay, so just press B. The keyboard. Excellent. Okay, now I showed you that I had liquid nitrogen over here. Liquid nitrogen is nitrogen gas, which is cooled to minus 196 C. And you can see there's a lot of white smoke coming out. Question, what is the white smoke?
The nitrogen gas is evaporated.
Now, if you remember your basic science, they said that nitrogen was a colorless, odorless, tasteless, etc. gas. If nitrogen was white in color, we would not be able to see each other because the atmosphere would be white. So it can't be nitrogen. Condensation. It's moisture. It's the moisture in the air that is condensing. So if I add moisture, what am I doing? I'm making clouds. there's enough dust in the air that can form particles on which you can get clouds. You must have seen this if you open your fridge on a very monsoon season or something, there's lots of water in the air. You may see this in a moist place. In Mumbai, you see it all the year. Very moist. Okay. So this white thing is not nitrogen, it's just water vapor in the air. Okay. Now liquid nitrogen is extremely cold, minus 196 C, 77 Kelvin, 77 degrees above absolute zero. If you touch it, you get burned. Okay, it's a cold burn, so we are very careful in what we do. Whatever we do is safe, don't worry. Okay, but I can use this to show you some things, what happens when things get cold. So what happens, for example, when a gas gets cold? I have trapped a gas here. I've trapped a gas, right? This is gas trapped. Okay. What do you think will happen when I cool this gas? The balloon will burst. What is this? Please talk. I can't understand this. It will become small. Let's see what happens. Okay. Now, by the way, when we do experiments now, and we'll do some hot experiments also later. See, the problem is you'll say, "Hey, the scientist from TIFR came and did an experiment." Sometimes experiments don't work. They say, "Hey, they did an experiment, it didn't work." Useless people. So what we will do is, sometimes we'll call you and make you do the experiment. Then if it doesn't work, I'll say, "Hey, it wasn't my fault here. Usko pata nahi how to do it." Right? So we'll blame it on you. Chalega na? You'll help me do experiments? Yes. Good. Okay. First experiment, we're going to take this. This I will do because it involves putting it inside. I'm not going to put my hand inside. I know what I'm doing. What we can do is for at least for those people who are watching it outside, we can go to Google Meet and can you pin my video because they can see what's happening then? You can't see it here. This is for those who are on the live stream. Can you just hold this? And just you're the camera. We can another balloon? No. Okay. Now we have a balloon. Can you see anything inside the balloon? Do you see some liquid inside it?
Yes.
Can you see some liquid? Can you see as the liquid is boiling, it's getting bigger? Okay, now what I want you to observe is that after some time the liquid will go away, but you'll see a white powder inside the balloon. You can already start seeing that there's a kind of a white powder. Can you see there's a white powder inside? And after some time that powder will go away. Can you get some leaves? Just get some leaves from outside. So the powder is also gone right now. Okay, we will do this one more time. We will make sure that the balloon color has nothing to do with it. So we try the blue balloon. So why did the balloon become small? Because gases will contract as you cool it. You cooled it so much that something in the balloon, the air liquefied. You had the liquid and it boiled off. When it boiled off, you were also left with something that was okay. We'll do it from this side. Can you see there's a liquid inside here? See a liquid? And it's slowly boiling off. And there is a whitish powder inside. There is something sticking there. See there? Inside there is something sticking there. And let this heat up. If there is any nitrogen left, we can label it later on. If there is any nitrogen left, we'll have a choice between tipping balloons or blowing up stuff. You can see which one you like. That's gone again. Powder is also gone. So tell me, what was the liquid and what was the powder? Now remember, when we breathe in the air has 21% oxygen, approximately 20%. We don't use all of it. We use only a few percent of it. So what you breathe out is approximately 16-17% oxygen, only 4% carbon dioxide. But oxygen is liquefying at minus 183. We need these ACs off. Right? That light, okay. Oh wow, we've got this on the screen. Fantastic. So you can also see things. Maybe what we can do is, for those who didn't see this, I'll try and show you this liquid thing again. We use this, it's a little lighter. Okay, now can you see the liquid inside? It's sloshing inside. Whoever is watching this. and it's slowly becoming bigger. And let's see if we can see there's some residue inside. You can see some of this residue which is sticking there. And the residue also, there's the residue. You can see the residue. And you'll see after some time that the residue is also going away. Warm it up, and it's gone. Okay? So hopefully everybody could see this, right? So, and hopefully all of you who are watching online, you can also see this. Okay, good. So that's one thing that happens. Now, so now let me do one more thing. Why don't you come here? And why don't you come here? Don't smile like that here. Come here, do some work. Good. Thank you. Yeah, you're also going to get it. Now just leave nice and soft. Feel it. Nice and soft. What are we going to do now? We're going to dip this leaf in liquid nitrogen. Okay? Watch what I do. I'm not going to dip my finger. I'm going to hold it by the stalk. Dip it in liquid nitrogen. And take it out. And now just do the same thing. Jaldi karo. You wait so long, it's not. I'll show you. If you take a leaf, you dip it in liquid nitrogen, take it out, papad. Don't try. Don't put your finger in, okay? Just the dip the whole thing. Yes, you see something here, and now crush it. Works? Very nice. Please explain why. Thank you. Tell me why this happened. Why did you take a leaf which was nice and soft? It is a leaf nice and soft. You put it inside. Okay? And it gets crushed. Yes, red t-shirt. Perfectly fine. You had water in the cells of the leaf. The water froze instantly once I put it inside. There was a very thin sheet of ice which is solid and you could crush it. Okay. Ma'am, why did you come up here? Yes, you, red t-shirt. Please. I want to say thank you to you. Okay, because you answered that. I don't know if ever anybody's gifted you a flower, but here's a nice steaming flower. Thank you. Used a lot in industry. Okay, so you saw how properties change. Now, hey, you know what? For your experiment, I think we need to put a nail. I think so, we're going to put a nail. Okay, banana. Yeah, take a banana. That's ridiculous. Can you hammer a nail with a banana? Put it in. Now, do you see that this thing is boiling very vigorously? See, it's boiling. Can you see it's boiling? Why is it boiling like this? Because you put a very, very hot banana. The bananas are room temperature. The banana is almost 300 degrees hotter than this. 200 and something degrees hotter than this. So it's gone in, it's sudden, it's like if you put a red hot object in water, the water will start boiling around it. So this, you have put a very hot object into liquid nitrogen, half the nitrogen is gone already, right? It's boiling because of, it's transferring the heat from the banana. Okay, there you see it's banana is in the liquid, it's boiling, and the banana is boiling. I think you should add some more liquid to it. Some hard. Okay. By the way, I took this example of playing cricket, no? Hitting a six. How many people out here watching cricket? IPL types. All of you a lot, yeah. Okay, I'll tell you what. How many of you are good batters? Put your hands down. How many of you are good bowlers? You guys are good bowlers. Okay. choose a banana. How do I? Let me just do one thing. Okay. Okay, guys, move. Go. I don't have a hammer. I have a cooker. Which I will use. But let's just. That's the banana. Okay. Oh my God. You see how the banana shattered? Okay. Properties of materials change drastically when you make them very cold. Okay. Now that I have a cooker, I might as well do an experiment with it. Let me see. Let's call some pictures out here. Hello, ma'am, checking your mobile phone in the middle of this. Ma'am, checking your mobile phone. Come in. She's got full-handed. Okay, ma'am. Welcome to the show. Are you a teacher? You teach science, maths? Maths. Very good. You cook at home? Have you ever used a cooker? You use a cooker? What, to beat people down? No. Okay. So, I have a cooker. Now, when you put a cooker on the gas or whatever, I mean gas name, I don't know how you put induction, jo bhi hai. Okay. How long does it take to get the city out? This is whatever. 5 minutes to lagte hai. It's a young person, so no time nahi hai. Let's do one thing. Let's see how long the cooker will take to whisk. Okay. So, what am I going to do? I'm going to take some liquid. Okay, I'm going to put some liquid in the cooker. And okay, ma'am, are you ready? Let's seal it. Is it a hot cooker? No. It's cold and it's listening. Why don't you go around and show people it's cold? It's listening. Okay, while that happens, bowler number 1, what's your name? Daushik. And what about you? Parinita. Daushik. So, as you are sitting, you are still not saying, okay. Extra काम बोल रहा हूँ. ठीक है. Who's going first? Okay, you're going first. We're not school. You're a cool guy, no? So you're going to the cool ball only, no? So we cool it. We'll take some time. This is cool. Okay. Why did the cooker start whistling like this? A little bit of liquid generates a lot of gas. 1 liter of liquid, 700 liters of gas. 1 liter of liquid, 700 liters of gas. So it generates a lot of gas. It can't come out because the vessel is in. Pressure builds up. Once the pressure is enough to lift the vessel, it happens very quickly. Okay. And you can see it's so cold that ice is forming outside. Okay. Meanwhile, Mr. Bola, Daushik, come in. Are you left-handed or right-handed? Right-handed. So I want you to check the bounce of the ball again. Okay. Okay. What you're going to do is you're going to there, far away from people, and just bounce it hard. Bola bouncer. Are you ready? Okay. Right-handed. Very good. Okay, good. Come, can you go ahead and I'll give you the ball, yeah. Either I'll just wait. Either एक जोर से bouncer मारते हैं, okay?
Sure.
वो जो अपने सर हैं सीसी से वो करे कि आज
Go for it. Hard. Bounce. Did that sound like a rubber ball? क्या किया था वो?
Glass.
क्लास के जैसे
What is that?
Cup.
You want to try? Now she's feeling good. Earlier, shall we repeat this? Yes. The ball is bouncing well. Yes. Good. So we have to make it cold first. So we उसको
इसके बाद तो आ जाओ ना.
Then it'll take a while for the ball to cool down. Just give it some time. So you can see the what is it? What's happening here? Getting cold. Is something boiling? What is boiling?
To make it boil, the water boils, the egg doesn't boil. Right?
The nitrogen is boiling. No, some people say
The ball is boiling. Ball is not
boiling.
boiling.
Nitrogen is boiling. Okay, good. So
Left handed or right handed? Right handed. These are special gloves so that you can hold on. They're cryo gloves.
okay. So you will also do this for safety far away from you. You can choose this corner, that corner, any corner. किसी को अच्छा नहीं लगता उसके मुंह पे जाके no whatever you want to हाँ okay ready okay we're doing the same this so take the ball this side okay do it this side so that side and go that's it पटाख से जल्दी जल्दी बॉल में बेटा बाउंस इट हार्ड इतना खुन्नस किस पे है
डोंट टच इट
good so now let's move on from we've done some experiments we'll have some more at the end what we'll do is there are some which are a bit dangerous to do here we'll go outside and do it okay we'll definitely go outside and do some I think we've done the one we can do here what we will do now is try and do some Olympiad level experiments problems so yeah can you go with my presentation please and give me light because I'm as long as you know 1, few and 10 you know all calculations you need you don't need any more numbers than that mostly okay and this is very useful for making estimates you want to figure out like is my answer correct I've got 23,000 liters should I check should it be 200 liters should it be 2,000 liters should it be 20,000 liters you can check this by just doing quick estimates okay now let's go to the next one so how are Olympiad problems different from the yeah that's good so in science it's very easy because the science questions are entirely based on what is there in the NCERT CBSE syllabus which you study. Science, no problem. Okay. I have seen you, I'll catch you. Next experiment you're going to come. Okay. And remember experiments are getting more and more dangerous as we go on. Right? Okay. Now, mathematics is where it gets a little different. Because in mathematics, the textbook mathematics is a very sort of useful mathematics, which is not the beautiful mathematics. The Maths Olympiad is about beautiful mathematics, not necessarily useful mathematics, useful in everyday life. And there are some very simple concepts which are not always covered in school. If you understand these concepts, you will find that most Olympiad problems fit in some of these standard concepts. The first one is something called the pigeonhole principle. The pigeonhole principle in many countries is taught in the 6th standard. I don't know why we don't teach it. It's a very simple thing. if there are 4 chairs, right, and there are 3 people, and only one person can sit on a chair, there has to be one chair with nobody on it, right? Pigeonholes are where there used to be little cubicles where letters were put. Conversely, if I have 3 chairs and 4 people, and all of them have to sit on one chair, 2 people have to sit. Have you got this? If you have got this, many Olympiad problems will reduce to this. I'll show you some. Then you have combinatorics, where you combine numbers and get things. You have some number theory ones, and you do modular arithmetic. Modular arithmetic is when you do division, but you don't care about quotient, you care only about remainder. And I'll give you examples of this. Okay, so let's go on. Next, please. Okay, so what is the thing? In many problems, you have to figure out how many pigeons, how many pigeonholes. Let's start with an easy one. In a group of 13 students, there are 13 students. If I ask everybody their birth month, right? At least 2 students have to have the same birth month. Is this obvious? Has everybody got this? If there are 13 students and I ask everybody their birth month, at least 2 students have the same birth month. Now let us phrase this problem slightly differently. What is the minimum number of students required to guarantee that at least 3 students share the same birth month? 25, correct. Because if you have 24 students, they could all have 2 in a month. If you have 25, there has to be a month which has 3. Now let's make it more interesting. So those are easy. You can see where the pigeons and the pigeonholes were. Show that in any set of 11 integers, there are 2 numbers whose difference is divisible by 10. Can you do this? Can everybody do this? You have 11 integers, any set of 11 integers. Now what you do is you check remainders modulo 10, you look at remainders. Any integer divided by 10, what can you get? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Agree? And there are some 10, there are 10 of these possible answers, there are 10 pigeonholes and you have 11 numbers. There are 11 pigeons. After this you can apply this and figure out what to do. So these types of problems, these are very simple, but these are all examples of the pigeonhole principle. Let's go to the next one. Okay. Now let's take a game. Okay. Take the numbers from 1 to 9. And every time you do one thing, you pick any 2 numbers A and B, erase them, and replace them with A plus B minus 1. You have numbers 1 to 9. I can write them on the board. Can I get some chalk?
Yes, sir.
I replace them with A plus B minus 1. 5 plus 7 is 12. Minus 1, 11. So I put the number 11 here. And you keep doing this. Okay. I do it 8 times. What's the answer? That's correct. It's very correct, very good. But everybody is not at your speed. So, in such problems, see, they are apparently hard. But if you figure out what to do, it can be very simple. Can you just hit enter one more time?
Yes.
What am I doing? This is much easier. I mean, he could do it in his head. It's much easier. This is like a mental math problem actually, because every time you are removing A and B and replacing them with A plus B minus 1. So what happens with the sum? The new sum is an old sum minus of A plus B, because A plus B is gone off. So minus A minus B plus A plus B minus 1. So the old sum minus 1. So every operation you reduce the total sum by exactly 1. So in 8 steps you reduce it by 8. Initially it's 45, 45 minus 8, 37. Whatever you do, you will end up to 37. Right? This is actually apparently a confusing problem, but it's actually a very simple problem. Now you can generalize it. This is obviously, I'm not going to do the, they won't, well, you don't get such simple problems. These are just helping us to think. I can generalize this to n. I can generalize this to, instead of a plus b minus 1, I can make it more, slightly more complex. But the idea is the same. The idea is keep it simple. Go ahead. Okay, now that was enough of maths. Here's the problem from the Junior Science Olympiad about candles. Okay, so in this you had a picture of a candle only, and you had some points, and they asked you where is it hot, where is it cold, etc., etc. So what we will do now is we will actually, before we get to this, so what is the thing? They told you what a flame is. They asked you from all these points 1, 2, 3, 4, 5, 6, which is the hottest part of the flame, which is the coldest part of the flame. Where is the water vapor the highest? Why should there be water vapor? Is there water vapor inside the flame? No. Yes. I mean, look, there are only two choices, no or yes. Yes. Why? Good. No. Why? If you say yes or no, you have to explain yes or no. Guessing is not a game. It's a game, but still, we're not playing a guessing game.
Okay. Yes. Why? I'm not sure. I'm not enough anyway. Let's see. What is a candle containing? Candle contains oxygen.
No, so candle requires oxygen to.
Candle requires oxygen to burn. Yes. Agreed. मान लिया. Good. Water vapor किधर से आया?
So candle is basically burning in air normally. So it will have some water vapor content.
It will have water vapor content.
Air has water vapor.
Air has water vapor content. That's like miserably small, right? But I'll tell you, when you're cooking at home, suppose it's a gas flame, you put a thing with cold water in it to make something, whatever. For the first few seconds, you see water contents outside that. Observe this at home. That's all observations. What does a candle contain? Candle is made up of what? Wax. What kind of a compound is wax? It's a hydrocarbon. What is a hydrocarbon? What does a hydrocarbon contain? Carbon and hydrogen. The carbon plus oxygen will give you what? CO2. And the hydrogen plus the oxygen will give you what? H2O, water. The water came from the wax of the candle. The hydrogen part of the hydrocarbon combining with the oxygen in the air gives you water. So candle plus oxygen is giving you some combination of carbon dioxide and water. So all flames from hydrocarbons will have water.
यहाँ तक सही है एक वहाँ पे जाने से पता नहीं कुछ तो माइक का पोजीशन सही नहीं है मुझे ऐसा शेल का बस नहीं चेंज कर सकते
There were some other questions on it, and there was a very interesting question. Please enter that there is another type of flame which is common in labs, Bunsen burner. They compared the two flames. Then somebody burned two different things in the flame and saw something happen. And from that, can you say which one was which? So we will try and do some experiments based on this. Let me introduce Krish, chemist, hardcore chemistry guy. Loves burning up things, including candles, burners, everything. He's ready. So he's going to show you something about the flame. But first we will observe a candle flame. So if we have turned that, you can light a candle flame here. Right.
What is it?
Candle.
What is it made of?
Wax.
Wax, right? And what is wax made of?
Hydrocarbon.
Yeah.
What is hydrocarbon?
Compounds are made up of
Carbon and hydrogen.
Carbon and hydrogen, right? How many carbon, how many hydrogen? Depends on the compound. So, for example, can you name some of the hydrocarbons? Butane. Any special use of butane?
LPG.
LPG.
LPG in India is mostly butane and propane. In other places it can be more propane than butane, but in India it's mostly butane.
So, methane, butane, they are all solid, liquid or gas? At room temperature and atmospheric pressure, gas, right? This is also, you said, hydrocarbon. This should be gas.
Octane, I'm adding more C's.
Yeah.
butane, pentane, hexane, heptane, octane. Octane. When is pentane a gas? Is hexane a gas? Or is hexane a liquid now? If I'm adding more carbons, making the molecule bigger, why is it becoming liquid? Hexane is a liquid. Okay, it's almost like it's liquid. I mean, it'll be boiling very low, but it'll be a liquid. Octane is definitely a liquid. Now, just as you said, butane was in LPG. Where is octane? Petrol. When you say 88, 92 speed, that the number is the octane number. What is the percentage of octane? Okay. By the way, they are mixing, now they want to make E85 and all this petrol. So they want to mix 15% ethanol. Is ethanol a hydrocarbon? Yes, no? Ethanol is a hydrocarbon or no? No.
जिधर जैसे सर जाएंगे घुमाना.
Okay. Now, is it only that this methane, ethane, butane, propane, they are one kind of hydrocarbons? Are there any other kinds of hydrocarbons? Yes, what?
So, like for example,
Propene. Ethylene. Propene. All the IUPAC. Look, IUPAC thing is only used in NCERT exam, nowhere else. No real practicing chemist of any quality will ever talk about IUPAC things. Have you heard of benzene?
Yes.
Right? Is benzene a hydrocarbon?
Yes.
Naphthalene balls that you put it in the.
Naphthalene balls that you put for mothballs. Is that a hydrocarbon? Yes. Why? Now this thing, this is solid, right? So what is the minimum carbons it has? Can you say?
Yes.
Can it have 8 carbons?
No.
Octane is 8, I know. Well, it depends. It depends because you are thinking only of straight alkanes, right? You could have 8 carbons and still be solid if it was some different structure, right? So, matches hai? Lighter hai? Okay, so yes, how many carbons typically in this? CHXY or how many C's? What about naphthalene? Naphthalene is a solid, no? Okay. Are there solids which have less carbons? Possible? Is camphor a hydrocarbon?
Yes.
It's like naphthalene, no? It smells. You put it in the cupboard, whatever. Okay, let's burn the candle.
So you have, let's start with gas, and then liquids, and then solids, but that evaporates very fast. That's naphthalene, somewhere, camphor. And then some solids that really doesn't evaporate, so it doesn't smell like naphthalene. So these wax are typically like a carbon almost 30. And so accordingly hydrogen adds to that. So almost 60 hydrogen.
नहीं सर पोजीशन उसका
30
नहीं
carbs.
थोड़ा ऊपर को.
So altogether it's a very gigantic molecule, big molecule, and that's why it makes it solid at room temperature. So we're going to burn this candle.
नहीं नहीं ठीक है.
the smaller candle to the bigger candle? Is it easier? Or is it just that I'm the cool guy and it's good? Or is it actually scientifically easier to do it for a smaller candle than a bigger candle?
Sir, because center of gravity of the smaller candle can be lower.
The center of gravity is at the same, it's on the axis anyway.
But the height will be different for the higher candle and the.
Hence,
As the center of gravity comes closer to the ground, the momentum will.
momentum. नहीं हो रहा है यहाँ पे.
Inertia.
Inertia. It's a torque. What you're looking for is torque. Anyway, छोड़ो. Now you're seeing the flame. There's still a draft on that side. I think we should close that AC. Okay. So now, why is the color different at different positions in the flame? Is this flame hotter than the flame of your gas at home? Does the color have anything to do with the temperature of the flame? I'm asking you questions. Okay, no, I think it's, if you take the whole thing and tries to normalize, you would go very close to the flame to get only the colors. Yeah, now you see the blue at the bottom? The bottom is blue. Okay. The other thing is this flame, how is this flame different from the gas flame at home? Or a Bunsen burner flame in the lab? Is there a difference? Differences in what? In color?
Yes.
Temperature? Why is this hotter? Are blue flames always hotter than yellow flames? Why?
The blue flames normally show complete combustion while the yellow flames completely.
Can you have a yellow flame which is complete combustion? You could, depending on the material. So just remember that there are some things which are colored because of their temperature, there are some things which are colored because of what is there in the flame. And here what I have is a transparent glass slide. It's just a glass slide, you can't see it here. It's a glass slide. Okay, you can barely see it. But if I keep a glass slide on top of this flame, nothing much happens, water condenses because there is a gas. We can switch this off. So, okay. But if I keep the glass slide on top of this flame, okay, can you see it changed color? But I need somebody to come here and observe this very closely, or you take the video from the top, because I want to show you that the flame is hollow. Okay, so I'm going to take another glass slide and I'm going to push the flame from top. You will see that the flame is burning only in the outside region. The center of the candle flame is hollow. Okay, so look at it from very close and from top. Top. Come closer, come closer. Let's try it again. Just one flame is better. It has to be steady. It's not vertical. Now there's that AC which is going on the draft is also. So you block it. Good. Okay, so can you see it's hollow in the middle? It's not burning in the middle. If I do it, if I flip it and do it. I'm going to do this quickly.
तीन सीन को स्विच करने की फैसिलिटी है कि हम
Which way
तीन इनपुट आएंगे हम कौन सा आउटपुट
You can do this at home. Take a glass slide. You see that the, can we have more light here? No.
Yes, okay.
Can you see this so you can see this?
हाँ वहाँ हाँ यस नहीं ठीक मैं कर लूँगा
Can you pin this video for everyone?
यस सर पिंड
Make your video. Can you see it is hollow? I mean, this part you saw a circular pattern, no? The carbon circular, the circular pattern. In the center there was nothing. The center is whitish because there is some unburnt wax in the middle. So wax is melting, it is going up the wick, it is evaporating, there is unburnt wax in the middle, and it's burning only in the ring. Because this flame, the oxygen is outside. There is no mixing of fuel and air. Unlike your gas at home or the Bunsen burner where you mix fuel and air and burn it to ensure complete combustion, here this is whatever oxygen can come from the side. It's called a diffusion limited flame technically. But the idea is oxygen comes from the side, fuel comes from the middle, it burns where they meet and it's hot enough. So in the middle, it is not burning. So that is one of the reasons you have these different zones. The zone of the flame which is just around the wick, there is no burning happening there. Okay. Now of course, remember hot air rises. So because of this, there is a current of air that is coming from the bottom and going around. Okay. Because of this, fresh air is coming at the bottom, which is why the bottom of the flame is bluish. Because that's why it's getting a lot of air. You see the bottom is bluish. Yeah? The bottom is bluish. That is why the air is coming, fresh air is coming at the bottom. The top is not that much. Why is it yellow? It is not, the yellow has nothing to do with the temperature. The yellow is because there are unburnt carbon particles. These unburnt, or burnt carbon, partially burnt, or whatever it is. Carbon particles are glowing. The soot that you see, this black that you see when you get it, these particles are actually.
So this is halfway burn.
Yeah, it's.
Just stop.
It stopped at C. So the C, particles of C are glowing.
So they didn't have a chance to go to that state. They stop at hydrocarbon, oxygen, and goes to carbon. That's why it looks black.
Okay, I'm going to show you one more thing now. I'm going to blow this off. You see some white smoke? And I could burn the smoke. When I burnt the smoke, the flame went down to the candle. Let's do this again. Thoda candle ke upar, thoda candle ke upar. That's fine. Okay. White smoke, and I can burn the smoke. I didn't touch the wick. I only touched the white smoke. The white smoke is vaporized wax. The wax is still hot. It is still vaporizing. So normally it would burn. But since there is no, I've reduced the temperature. It's off. There's white smoke. I burn the smoke. Could you see that? Okay. One more time. Side से. दिख रहा है? But I can't see.
कुछ yes, no, बोलो कुछ.
So that from a distance I could light it. And the flame just jumped to the wick. Okay. Anyone's birthday today? Anyone's birthday this month? You said people with birthdays this month, or at least
This month हुआ.
this month होगा ना? Happy birthday this month. Why does the flame go off when you blow it? See here. Birthday पे क्या करते हैं? Happy birthday to you. Okay. Now, why does the flame go off when you blow it?
Because of the air.
Birthday boy, bolo.
Because of the
Okay, let birthday boy speak. No, he's behind you. Your birthday also this month?
Yes.
Oh, okay, then you also done. Yeah.
The air you blow, like it has CO2, so.
Fantastic! Just the wrong answer we wanted. Wonderful. Next. 6 8, don't stand. Now I told you it's not CO2. So, let me show you it's not CO2. Do we have a pipe or a straw or something? I don't know if you've ever gone to a guy who makes gold things. They blow with the. If I blow, even the 16% oxygen in my breath is enough for a candle to burn and to burn brighter than it would burn as long as I supplied air. So I make the candle go bluer by blowing on it. Okay, let's try this. See, the region of blue increases. The region that is blue is increasing when I am blowing on it. I could make it completely blue before it went off. Okay. So the thing is, 4% oxygen in your breath is not sufficient to blow off the candle. The candle can happily burn. By the way, outside there were some glasses. Now this candle is becoming small enough that it can cover to the glass. So that is another classic misconception of why candles go off when they are covered with glasses. If you can get a glass. Okay. So what did we say? We said that it's not carbon dioxide. You need 3 things for a flame. What do you need? You need fuel, you need oxygen, and you need high enough temperature. When I blow, I cool it down below the temperature at which the wax can burn. That is why it goes off, not because of the carbon dioxide. And by the way, if you come to HBCC, we can show you that there are things which can burn in an atmosphere of 100% carbon dioxide. If you burn magnesium, it will burn brighter in carbon dioxide than in air. There are many things will burn in carbon dioxide. It's not the carbon dioxide necessarily that puts it off. A flame like this, we will see what happens. Okay, now the question is, where is the flame the hottest? At the bottom, at the top, in the middle? Can you come? Actually, आप ये side आ जाइए so that you don't block me. So which part of the flame is the hottest? At the bottom, in the middle, at the top, just above the top? Bottom, top. The bottom blue part. Or is it in the middle somewhere? How hot is this? Is it 200 degrees, 1000 degrees? Okay. Okay. Next, the problem asks that somebody burned two things. You have some naphthalene? Okay. So what we have is, we have some naphthalene and we have some citric acid and we have two glass dishes. Unfortunately, Krishnendu is a very good chemist, but he's forgotten to write which is which. He's forgotten to write which is which. So he doesn't know which one is naphthalene, which one is citric acid. They are both white powders. White powder number 1 and white powder number 2. And he's pretending that he doesn't know which is which. Very good. Okay. So now what we're going to do is we're going to burn them. We're going to take a stick and we're going to burn it and see what happens. And that was the problem. That was the JSO problem, was if you take a...
So about this, I'm closing my eye and you can just mix it. Yeah. That is the real science. Yeah. Then I have no clue which one is which.
They look very similar.
Very, very similar.
So he's going to just heat his rod so that can stick to it. He's going to touch some of this. That's not a good idea because you've got... yeah, just use a little water to pick it up. Because the point is it doesn't stick to the glass rod at all. And I can't put a match in the flame or something because that would change things. Okay, so he's now got citric acid on the... No, he's got something on the rod. No, I think, I don't know. It's melting, it's dripping. Well, okay, you saw how it behaves. Let's try the other one. The rod. Now he's picking up something. Can you focus on the flame? See, this one's burning. You can see it's burning on the rod. Can you see the stuff on the rod is burning? See, it's burning on the rod. There. In the other one, it didn't burn on the rod. Try the other one. Probably melting. You can see it's melting. There's a drop out there. It's burning a little bit, but not much. There, it got some fire, it got some sparks, and it's gone. It's sparking a little bit, more than really burning.
just for the amount of burning and the amount of blackness.
Can we get the lights on?
So we have two different rods.
Can you see two different rods? Now you can see this, right? We just do this for the online audience. This is one rod and the other rod is. So you can see there's two rods that both of close. They are very differently black. One is black everywhere, one is not very black. Which one is naphthalene, which one is citric acid? This is your standard, we took the problem from 2021 JSO. Exactly the problem, it asks you where was the candle the hottest, where is the water vapor the maximum, and then it did this experiment and asked which one is naphthalene, which one is citric acid. Naphthalene is C10H8. Naphthalene C10H8 and citric acid is C6H something O.
H8 and O7.
O7.
So both compound has lot of very similar number of carbon, very similar number of hydrogen. The only difference is that one compound has bunch of oxygen and one compound really lack of oxygen. So which one is which?
So see, the guy who had his own oxygen did not generate much carbon. Maybe. The one who didn't have,
Everyone is on the board, right? So if the first step is go to carbon and then the second step go to CO2. So one compound has a lot of oxygen inside it and one compound really is going to the air to get oxygen from it. So who has more probability to go to all the way to CO2 and who will stop exactly at carbon?
Exactly. So the naphthalene is the guy that's blackish, generated a lot of carbon, the citric acid had much less carbon. So this is logically finding things out. Okay, great. Now, you can stop this. You can stop this, we're not. Oh wait, you can try the thing. We have one more one. Can I try this? Okay, what happens when I cover a candle with a glass? It will go off. It didn't go off. You didn't say after how much time. By the way, you can see there's black stuff here. And if you notice, okay, I'm going to do it one more time. If you notice, this part is wet. There's water here. That's that H2O coming from the flame. It's wet. If I take a new glass, see it's very clear. This is not a good glass, but you can see here it is clear, right? It's clear over here. Let's see what happens. There is water condensation here. It's much. People who are close by can probably see it. It's difficult to see it from on this camera, but with your eyes you will see that there is water. There's been water condensation here. Now, if I keep it for a long time, what's going to happen? कवर नहीं किया था हीटिंग है ओके ठीक है अभी पूरा कवर Why did it go off? Because the lack of oxygen. Again, not the right answer. Again, not the right answer. Now, can we make a small candle? Cut this one. No, cut this one.
ઊભી
Okay, so now we have
Oh, shit. रिकॉर्डिंग में जा रहा हूँ
अर्नब सर आ जाओ।
ज़्यादा एक्टिव होता है तो टीम मेंबर्स परेशान रहते हैं। बेचारी बैटरी
now I have two candles. The original candle is still there, right? I'm going to repeat this experiment. Now can you see two candles? The first candle is gone off. The second candle is still burning. The same candle went off. It took a long time for the second candle to go off. So when the first candle went off, there was enough oxygen. Oxygen had not got over. If you notice the first one is still, the second one is still smoldering that white wax. We can do it once again. So these
गर्म C2 गर्म
See, these days we are not allowed to do experiments because of various ethical concerns and all. So Michael Faraday gave a series of lectures called The Chemical History of a Candle. In that, they used to take a big bell jar, put a candle, put a rat. Candle would go off, the rat is still happily running around, which means oxygen has not got over. These days, animal ethics and all, you can't do these things, but it's definitely not oxygen.
पूरा बर्न हो गया होगा उसको थ्रेड।
In this case, you should think of your answer. I'm giving you a hint. Birthday pieces.
सर ये थोड़ा उठाएंगे।
किसके ऊपर फोकस किया हुआ है हर्षा जी ने? हर्षा हाँ सही है।
Vic has gotten stuck in the. Problem one, this candle deposits wax on it. Depositing more wax. Okay, now you have two candles. We can repeat this experiment. Repeat. We take this glass which is less dirty. First one went off, second one still burning. Now the second one went off. Okay. So why does a candle go off when you cover it?
Does the carbon dioxide get accumulated?
Carbon dioxide is a denser gas than air. But yes, you are right. It is hot carbon dioxide. Carbon dioxide and air at the same temperature, carbon dioxide is denser than air. But the carbon dioxide being produced is hot carbon dioxide, it rises. And it slowly tries to fill this thing with carbon dioxide till the point where the flame is then shut off because of the carbon dioxide that's accumulating. It takes longer for the carbon dioxide to accumulate to the lower level till the bottom one goes off. And when we covered both, the top one went off quicker because the carbon dioxide from the lower guy is also accumulating on top. So it blankets with carbon dioxide quicker. But oxygen is not getting over. And then we can show this with some sensors for oxygen, whatever else. It's not oxygen depletion that is putting off the candle when you cover it with the glass. This is one of the major misconceptions in middle school, high school science. Okay, it's 10:45. Should we do some? Which one? Yes. There's one more thing we need to show you, the candle. Okay, which you probably have never seen. I have not seen an Olympiad experiment based on this as yet, but it gives me ideas. And if it gives me ideas, there might be an Olympiad experiment that comes. So we will light the candle again. But first, we need some volunteers. Who has not volunteered so far? Let's see.
This side.
Yeah. Let's get from this side.
You can come.
And ये जैकेट वाला आदमी आ जाओ. You look very cool and all. You're from?
तो मैं भेज दूँ
8CS2 Kalpakam. Kalpakam is 2 ACS. Okay, and you're from?
ACS4 Mumbai.
ACS4 Mumbai local. Ajawad. Now, what we have here is, where is the camera? Is a multimeter. Okay, a multimeter can measure voltages, currents, resistance, whatever. We have a multimeter. Okay, and this way. You can see the multimeter when we turn it on with the current range. There is no current. Can you see zeros? Yeah, we need some light on this. Yeah, just hold it there, and you guys will come here because you can see it. In case you have to shout out the reading. What's the reading?
0.
Okay, can you all see the reading now? Yeah? 0. Okay. So what have we done? We've connected the leads to two.
Yes, sir. Yes, sir.
So there's a battery, there are 2 spoons, and obviously no current is passing because the spoons are not connected. Can you connect the spoons? Touch the spoons. So you see, quickly goes to overload. Too much current flows. 6 point. You see some numbers. Current flows, right? Okay.
L for overload.
OL is overload. So yeah. So you see 11, 6, whatever. Some current is flowing when I touch the spoons. When I short circuit them. Okay. Good. Now let's see what happens. Now no current flows because they're disconnected. Is a candle conducting or not conducting? The flame. Conducting. Why? Because there's wax in it. But wax I thought was an insulator. Okay, let's see. Let's do the experiment. I can hold on. Okay. So what do you have? You guys have to shout the number. Okay. I need to give you some space. Yes, I can. I'll go here. Actually, now I think you don't even need this. The light is good enough. Ye kiska phone hai? Yes, sir. You can keep this one. You can see the reading, no? Okay. So now try. That's okay. It's okay. You want a nice big flame?
Yeah.
Yeah, but I sort of you have to give some time for the wax to melt because I covered it with the glass and all.
So what is the reading right now? How much current is flowing?
0.
How much current is flowing now? 1. Why is it changing?
Current is flowing.
Current is flowing.
Air is ionized. Bapre, it's only 9-volt battery. Yeah? The
This-
current is flowing because it's touching the spoons. The current is flowing through his body.
So we are also very good conductor of electricity. We get shocks, right?
Okay, so don't touch the spoon, touch
Don't
only the
touch.
plastic. If you touch the
Now I-
plastic, then
Touch. Now what is the current?
0.
Back to 0, right? So I am kind of holding this close. Still
0.
0. Now with this close, I'm going to get the so okay, back to 0. You have to shout. Yeah. Now. 0.1.
I think you should try a hotter flame, you know.
Yeah.
Yeah, we will try a different flame.
Do we have a hotter flame here?
Yeah, I mean, this is 0.1. Let's try a hotter flame.
Same thing back again. How much current? 0, 0. Then
0.1.
You're far away. Things are quite, you're not in the same vertical.
0.3.
4, 5. So how is it that the flame is conducting electricity? Okay, I think they're convinced the flame is conducting electricity. By the way, it's not just spoons, you can try copper strips also if you want. You want to try copper, you can just try copper. You have 2 copper strips. So now he has copper strips. And he's going to bring them near the flame. Close to each other. Still 0. 1.
how much is?
And you can see there's a